So this talk might be a little bit different from the other ones we've seen. Instead of talking about new architecture, I want to go back to the architecture we already have. So why am I here talking about precise exceptions? I mean, it's 2025. Surely we dealt with this decades ago. Well, let me give you a bit of context about what we're trying to do. So we are collectively programming language people. We're a bit outsiders to your group. And we're interested in programming language implementations and the software you build in them. In particular, well, for the purpose of verification, really. In particular, we're interested in our low-level software infrastructure, that which interacts more directly with the hardware, things like your hypervisor and operating system kernels, but also the more esoteric parts of our infrastructure, like our programming language runtimes and their JITs. These also are a bit strange, but they interact with the hardware in sort of the same way, and exceptions form an important part of that interaction. In particular, you have exceptions like interrupts for communicating with devices, but you also have exceptions on the boundary between pieces of software. So if you want to reason that these critical parts of our infrastructure are correct, then we need a good foundational model for the hardware, which contains the behavior of exceptions, of what we'll see later as precise exceptions. Now, we don't necessarily want a model of a particular piece of hardware. What you want is a really good model from the perspective of software. So that's what we really want, is an architectural specification, something that describes not just one implementation, but what all of them could do. So this is your x86 or ARM64 or whatever. There are many implementations, but they all must satisfy the same spec. And if you think about it, what is an architectural specification but a kind of set of instructions plus some behavior of how to compose them together? It's just a programming language. Now that might be a bit blasphemous to say to a crowd like this, but it's kind of true. And so what we're going to do is try to employ our programming language tools and techniques at the level of the architecture specification to try and reason about software. And working at this level is quite nice because we can essentially forget about the complications of hardware and focus on just the guarantees needed for software. And in particular, when we're thinking about exceptions, there are a number of things that software rely on. Now, you have the obvious things that if an exception happens, it happens in the right place for the right reason. But there is this one principle that keeps coming up over and over again, and that is this idea that the exception should be precise. Now, if I say precise exception to an audience like this, you probably have some definition in your head that looks something like this. So this is what you see in Hennessy and Patterson today, but also I think 30 years ago. And it has this nice double negative. I don't know why they like this, but it says an exception is not precise if the state does not look exactly as if the instructions were executed sequentially in order. Now, this property turns out to be really important for software. It's what guarantees that the hardware will not lose information when it takes an exception, and this is vital if you're doing like some page fault handling or some trap to emulate some instruction. But you've probably all seen this, and you probably saw it in many different forms. This is not unique to the Hennessy and Patterson text. This text dates back, I think, to the IBM System 360, like Model 91 from the 1960s. To today, basically unchanged. And this is really nice for software perspective, because you have this one nice property that it's relying on that hasn't changed, but hardware has. Hardware has changed massively over those decades. You become these high-performance, super-scalar, multi-core, multi-level cache machines that have become very, very aggressive. But that text, it was normative text. It was not describing how hardware was implemented, just an illusion that it was supposed to portray to software. So maybe it's okay, but one of the things this very aggressive hardware has been doing lately is exhibiting this thing called weak memory. That is, some of the optimizations you have deep down in the core that do out-of-order execution become observable to the software that's running it. So a classic example of this is in ARM. So if you have like one thread performing some writes, another thread can observe that those writes are happening out of order by just reading the values and seeing what it gets. Not through some timing or side channel, but by just looking at the values, it can see that some reordering has happened of either the writes or indeed the reads. And on ARM, this is perfectly allowed. So here we have these two things. We have some nice normative text that tells you the instruction should execute sequentially, but then we have these high-performance machines that are actually giving you observable out-of-order execution. And how do you rectify these two things? You know, one of the natural questions you might have, has a gap formed between our nice normative text that we've been using for decades and that software has been relying on, and the reality of hardware implementation? And how could you know? So let's look at not some Hennessy and Patterson, but look at what we actually find in some modern microprocessor architecture textbook. So this is an excerpt from the ARM Architecture Reference Manual, ARM. I picked ARM not for any particular reason, it's just that we're in Cambridge and ARM is in Cambridge. I don't think ARM is very particular in this case, but you will get something different if you try a different architecture. But this text is probably pretty familiar. It says an exception is precise if the register and memory state is consistent with having executed all of the instructions up to where the exception was taken. So it's not exactly the same words as the text we just looked at, but basically the same. If we're thinking about how this out-of-order execution, this weak memory, could interact with our exceptions in our software, then it's this word executed that causes us some concern. When you see this in the architectural textbook, what does it mean? Indeed, how could you even find out what it means? This is the definition. And if you think about it, anytime you see normative text in a textbook like this, in a reference manual, there are two possible interpretations. There's what is the architectural intent? What did the ARM chief architect have in his mind when he wrote this? But then you also have, how is this realized in hardware implementations? Now, I'm not saying that one of those is more important than the other, but in the end, you'd need to understand what hardware is actually doing to be able to build a sort of foundational model that you can believe in. And it turns out it's actually quite hard to know what many implementations are doing. People don't write down exactly how their implementations work, not in detail. Sometimes the designs are secret and they won't even talk to you. So in reality, the only way you could really know is to go out and buy a bunch of ARM hardware, build some complicated test harness, run a bunch of tests, and collect a bunch of data. Now, you may say that's an awful lot of work for one word in the middle of a 15,000-page document. Who would be crazy enough to do that? Well, that's what we did, and this is what we found. So this is quite a noisy slide. Let me break it down for you. So this is an excerpt from some of our results from running on a bunch of ARM devices. So each column is one of the devices. And we ran on things from like little Raspberry Pis all the way up to the AWS Graviton instances, the big server clusters that you get these days. Each row is like a little test program. If you're familiar with litmus tests, that's what it is. But these are little programs designed to sort of tease out a particular out-of-order behavior that you may or may not expect to see. Now recall our normative text said you should never see this, that things should have been executed or sequentially, it should look sequential. But you notice that some of these are underlined in red. These are places where we saw some out-of-order or some behavior consistent with out-of-order execution across exception boundaries. And this was surprising because the text told us we shouldn't be seeing this. But maybe it shouldn't have been surprising. After all, ARM has this sort of out-of-order execution, even without exceptions, and maybe that's all we're seeing. So I want to give you a kind of an idea of the kind of interactions that we're seeing in ARM, because really what we're seeing is not just, what we're seeing is a lot of interactions between exception machinery in the hardware and all of the other out-of-order machinery going on. And I just want to give you a taste of what that looks like. I'm not going to go into all of it in detail. So the first of these is something that, that if you're like a RISC-V person is probably a bit foreign, so I'll try and walk you through it slowly. But this idea of context synchronization. So if you update the system context in ARM, so you write to a system register, this may be surprising, but that doesn't take effect immediately. You actually have to do explicit synchronization before that effect will take place. And it turns out exceptions do that synchronization for you. So you get some nice sort of thread local synchronization when you take an exception, enough to show this. But as a side effect, it means that exceptions also wait for control flow. And this is a restriction on speculation, on some kind of observable level of speculation. And this seems to drop out of nowhere, I suspect. That text that we were looking at earlier seemed to have no connection to anything about speculation. And yet it turns out this is a thing that software is actively relying on today. Like inside the Linux kernel, you will find comments saying, oh, by the way, we're relying on this. And so it's really important that we understand these interactions if we want to reason about our software and not just hope that it works. So let's look at another fun example. So on ARM, if you have like loads and stores, they can be actively reordered, right? So if they're not to the same address, the ARM core will happily propagate the store before it satisfies the load. But it turns out, as I'm sure you know, loads can fail. They can sort of fail externally outside of the core because of things like ECC or whatever. And the system can report these failures in one of two ways. It can sort of report it asynchronously and say, oh, something went wrong. But it can also report it synchronously. And more often, we're seeing these big server cores want to report as many external errors as they can at the instructions that they come from, as this really helps with their uptime. But it turns out that if you report things synchronously at the load, in this example, then you actually can't propagate that store speculatively, early. And the reason is that if you did that, you wouldn't be able to take the store back, right? It sort of is, in a sense, speculative at that point. And this is interesting because here you get ordering, sort of memory model sort of ordering, that didn't exist in the original model and isn't happening because of an exception, but because one might happen. So that's kind of interesting. It might not be super surprising at this point, but it's kind of interesting that you get this kind of implementation-defined behaviors giving rise to ordering or not. But more worrying if you're in the other case. If you're loading from memory and you can only fail asynchronously, then you can propagate that store early, even if there's a precise, or a so-called precise exception in between. But what happens if the load actually fails? You really do get an imprecise exception, and that imprecise exception could happen after you've even propagated the store. But now you're left with this really horrible problem of sort of architectural text, is what did it mean for that exception in between to have been precise? Right? The load that happened earlier might never have completed. It might never have written back its registers. What is the register and memory state that the text was talking about that the exception handler sees? There doesn't seem to even be a way to write down architectural text that corresponds to this. And so, all of this leaves programmers asking, in 2025, what guarantees do precise exceptions give you? And it's a good question, and maybe we don't know anymore. There used to be some text that maybe 30 years ago hardware really did implement, but hardware has sort of diverged from that text and that architectural intent. But we do know something. So for ARM, we now have a pretty good idea of the interactions between the memory consistency model and these exceptions that give us a good bound on what precise exceptions can and cannot do. So I can't give you a definition of this, what it means to be precise, but I can tell you that this is what a precise exception gives you. There's a subtle difference. And hopefully this will allow us to sort of bring the architectural text back in line with implementations, although it would still be nice to have a proper definition. So for those of you that are interested, you can take those interactions and write it down in one of these nice memory consistency models. If you're not familiar with these, it doesn't matter so much. But the point is that, again, this is a model of the interactions between various parts of the exception machinery and the rest of the memory consistency model. It's not a general purpose definition of what it means to be a precise exception. So what's next? What is there left to do? Well, quite a lot. So first of all, we don't know if software is correct anymore. We would like to know if hardware actually implements the behaviors that we talk about here. There's only so much that sort of black box testing of hardware that you've bought online can get you. Somebody has to actually go and look inside and understand what's going on to tell us whether we've missed anything. And then finally, it would be interesting to know how the architectural texts for other architectures stack up. Are they equally as divergent from their implementations as ARM was, or are they a little more consistent? And indeed, they will be differently. We already saw one place in RISC-V where they'll have a different answer than ARM. And so I'm going to end with a kind of open question to you, which is, 30 years ago, there was this nice uniform definition of precise exception that software was relying on and has continued to rely on. Is there a path back to that? If all of them have diverged, not just from each other, but from their implementations as well, how do you get back to that state? I don't know. And really, it's up to you. So I'm going to end there. Thanks.